So as we're writing our quantum numbers, I want you to remember that these are really just subscripts in an equation. It's just there to help us keep track of the variables, and it turned out to be a really useful address system for talking about each individual electron. And these quantum numbers really do make an address system very similar to your mail system, either at home or in a dorm or wherever you're living. But, like all patterns, that can be tricky to learn and to understand. This is one of the techniques that I use to help explain that, and I like to call it the chessboard. Now, if you look over here, on this side we're going to have the size of the atom. And this is going to be given by our principal quantum number, n. Remember that n, we said, is allowed to go from, let's see, I'll just write it kind of over here. It's allowed to go from 1 all the way out to infinity. So I'll just leave it as the ellipsis right there. Now, this shape is usually going to be given by the quantum number L. That quantum number is called the angular momentum quantum number. Now, that's going to tell us our shape. The rule for L is that it goes from 0 all the way out to 1 less than whatever your n level was. We're going to make that make some sense here in a second. Our third quantum number that we talk about is m sub L. That is going to be whatever we have for L around 0. So we'll have negative L all the way out through 0, all the way out through positive L. Now let's see how all that builds into our chessboard. So if n equals 1, the only option L has is to be 0. And ml is always going to be around the number 0. So we're stuck with 0. That's going to be a very simple one. And I'll point out for those of you who have read ahead or know a little bit about this, this is going to be the 1s orbital. And it's just the very first ball around it. And it's why hydrogen and helium cap out at having a total of 2 electrons. That's jumping ahead a little bit, just to tie things together for you. If that didn't make sense, just keep watching. You'll see it soon enough. Now suppose that we go up to quantum number for principal equals 2. We're going to have L equal either 0 or 1, because remember, it's going to be from 0 all the way up through n equals n minus 1. So if it's 0, again, my only option for m sub L will be 0. It's got to be 0 plus or minus L. 0 plus or minus 0 is 0. But what about this one? This is where things finally start to get interesting. If n equals 2 and L equals 1, I plug that in here and I say I'll have negative 1, 0, and positive 1, which you see popping up right there. So we're going to have 3 different orientations for these shapes. Now we're starting to have some patterns. Now I want to emphasize that if I have enough electrons to get up to these quantum numbers, that means that I had to fill in all of these first. So I'm going to have a bunch of sets of quantum numbers. Always remember that the quantum number you're talking about is usually going to be the top electron, like the furthest out in the shells. But all those inner electrons still exist, and they still have quantum numbers too. It's just that we're talking about those outermost electrons because that's where you're stealing them. That's where you're adding ones in and getting new quantum numbers. That's where a lot of the action happens. But those inner shell electrons still exist. Now let's keep with the pattern for a second here. If we go down to n equals 3 or n equals 4, just like before, we're going to have our innermost shell. And that's going to be L equals 0, which means ml has to equal 0. And just like before, if we go up to a quantum number of 1 for L, then we're going to have ml be negative 1, 0 to positive 1 for the exact same reasons we brought up down here. But remember, if we're at n equals 3, this quantum number, L, can go all the way up to 2 now. And for 4, it can do 0, 1, 2, or 3. Let's see what those boxes are going to have in them. So if we're in L equals 2, plus or minus 2, around 0. So negative 2, negative 1, 0, 1, 2. And same thing here. And then finally, when we put this one in, we can have negative 3, 2, 1, 0, positive 1, 2, 3. Those are one of the ways that we can keep track of all of our quantum numbers. I also have a separate model that you can look at that tells us something that I like to call the address system.